Hello, this is Mr. Van Scoy. This is lesson number 4 on the stars, ES essential outcome number 7. In this lesson, we're going to explain the reactions taking place in the sun and in other kind of average size stars. So when you are done with this lesson, you should be able to explain those nuclear reactions taking place in the sun. In some of our previous lessons, we took a look at those different layers of the sun and also discussed atoms. If you aren't familiar with the different parts of an atom and the layers of the sun, I recommend you going back and taking a look at that. Here's just another diagram as a quick review of those different layers. We had mentioned something at the center of the sun in the core called nuclear fusion. That's what we're going to be mostly focusing on today. There are two basic types of nuclear reactions, fusion and fission. Fusion comes from the Latin fusio, meaning to pour or melt. Fission, with a F-I-S, comes from the Latin physio, meaning to split. So nuclear fission is going to produce smaller atoms and other materials or particles from splitting the nucleus of an atom. So it produces smaller atoms and particles. Nuclear fusion, on the other hand, is going to produce larger atoms from collision of smaller atoms or smaller atomic particles. I'll focus most of our discussion on nuclear fusion because that's what happens inside the sun. But I also want to talk briefly about nuclear fission. You are not going to be expected to know all the details of fission, but I do want to go over a few things with you. So let's take an element, for example, uranium-235, and we can split that atom into uranium-238 and uranium-235. There's also some other processes going on, but I'm just going to very quickly go through that. The products or results of that nuclear fission process is going to create free neutrons. It's also going to make or release gamma photons or gamma rays, which are harmful to biological materials. Recall from biology or biology 101 here, you are made of biological materials, and therefore the gamma rays that are released are harmful to people. It also releases a very large amount of energy. The elements that are left over from the fission process are also radioactive for many thousands of years. Again, also harmful to people. Okay, so why mess with this? And also, you might be thinking, we live in Michigan, we don't have to deal with this. This is something they deal with in the bigger cities or, East Coast, West Coast. Here in Michigan, we also have nuclear reactors. Here are the Fermi 2 nuclear reactors. But why are we messing around with this? It sounds like a pretty dangerous process, and it certainly can be. Like any kind of hotly debated issue, there are usually, there's pros and cons to both sides. If the radioactive leftovers in the plants, nuclear power plants, are handled properly, it is safe. It doesn't automatically mean that it's going to pollute the water, pollute the air, or the land. It does not produce greenhouse gases, and it produces a lot of energy in that fission process. That energy is then used to boil water into steam. That steam turns large turbines of wires and magnets, which then generates a lot of electricity. Keep in mind that there are different variations of nuclear fission, and not all nuclear power plants are set up exactly the same. Some are safer than others. And engineers and scientists have also developed different processes over time. On the downside of that is that not all of these plants are safe or as safe as they could be, and there are sometimes accidents. And again, the leftovers or waste is harmful for many thousands of years afterwards. People have also figured out how to do this with nuclear power, with nuclear weapons. All right, now we're going to do a quick chemistry review. An isotope is a chemical element that has a different number of neutrons. Remember that it's the number of protons that defines an element. Having different numbers of neutrons does change some of those properties of the element, but it's essentially still that same element. Okay, it doesn't matter how many neutrons there are in an element. If there's one proton, it's hydrogen. Doesn't matter how many neutrons are in that element. If there are 2 protons, it's helium. If there are 3 protons, it's lithium. Okay, when you have different versions with a different number of neutrons, we call that an isotope. They are still essentially the same element, and that's because the neutrons don't have a charge. All right, now we're going to take a look at a couple elements in particular, hydrogen and helium, and take a look at some of their isotopes. So here we have hydrogen 1. You know, it's hydrogen 1 because of that 1 up there. That's not the same. When we talk about isotopes, sometimes the number will be the same with these smaller elements. Sometimes that number will be the same as the isotope, but actually for most of them it doesn't. Hydrogen, because it's H1, just happens to be the same one. Okay, but when we talk about hydrogen 1, we're talking about 1 proton and 0 neutrons. So there is 1 atomic particle, in this case a proton, at its nucleus. And we're going to kind of leave electrons out for this discussion today. In hydrogen 2, there is 1 proton and 1 neutron, so that's a total of 2 atomic particles in the nucleus. It's still hydrogen though, because it's 1 proton. Hydrogen 3, as you might guess, 3 atomic particles in the nucleus. Again, it's still hydrogen because there's 1 proton. Helium 4, also just kind of might think of as normal helium. There are 2 protons, 2 neutrons, a total of 4 atomic particles or subatomic particles in the nucleus, so that's why it gets that H4. Helium 3. Helium 3, I don't have a slide for, but helium 3 would only have 1 neutron, would be short of one of those neutrons. Okay, so now we'll actually take a look at the nuclear fusion process. Okay, now I want to say right up front 2 things. One, that this is an overly simple nuclear fusion diagram, an oversimplification of it. However, for our discussion, this will work. I'm going to go into more detail, but if any point your head starts hurting and you start scratching your head about nuclear fusion, come back to this slide. It's overly simple, but it works. The very, very basics of what's going on in fusion. We have hydrogen colliding over here. We have 4 individual hydrogen atoms that are colliding and going to form helium. Okay, that also produces a lot of energy. Okay, and that's a 1 helium. So 2 protons, 2 neutrons. So that's why it's H4. All right, now I'm going to go into a slightly nerdier explanation of nuclear fusion. It might seem like it's a lot nerdier, but trust me, this is still a somewhat simple explanation of nuclear fusion. There are actually different pathways, but we're going to focus on one. Okay, in nuclear fusion, again, the slightly nerdier version, keep in mind that nuclei have a love-hate relationship. At low speeds, they have electromagnetic repulsion. Okay, repulsion means that it isn't, when something's repulsive, doesn't just mean that it's gross. They actually push each other away. They repulse one another, pushing you away. That prevents the collision of their nuclei. Okay. At high speeds, the nuclei being more than one nucleus, the nuclei come close enough that strong nuclear force binds them together. So low speeds, repulsion, high speed, attraction. When two atoms are pressed closely together, they collide with enough force. See in this diagram here, they collide with enough force. They release energy. They release a subatomic particle called a positron, and they also release neutrinos, another subatomic particle. Both of those kind of interesting in their own right, but that's a different conversation. They also produce an H2, one proton, one neutron. So that's a hydrogen atom. When we have one H1, the simplest hydrogen atom, collide with enough force with one H2, again, you have energy. You also have gamma rays that are released, and you have an H3. So we've actually created a helium atom now because we have two protons and one neutron, both of these particles into one. So we now have an H3. If we have two of these H3s that collide, okay, I've kind of been focusing on this one half, okay, as with anything in chemistry, this is just one simple atomic collision, but like in any chemistry, you have lots of chemical reactions going on in any given space. So if we have a couple of these H3s that collide, okay, you end up with an H4, which is a H3. My understanding is that H3 helium is quite stable, but then we have a more complete H4 here. I'm sorry, He4 helium. So it's got two protons and two neutrons, and then the protons are given off, leaving this hydrogen, those single H1 hydrogen atoms, as a byproduct. And then these can go on to continue the chain reaction of colliding and starting that process over again. That is why inside of a star, like our sun, we find that it's made mostly of hydrogen, approximately a 3-to-1 ratio of hydrogen and 1 part helium. As I said, there are other pathways in more massive, bigger stars than our own. There are other nuclear reactions that take place that create the heavier elements. As my note says here, relax, this is just for reference. Just wanted to kind of throw that out there. I wouldn't expect you to know this. Again, if this is seeming like a bit much, I have this simple diagram here. Again, keep in mind at a very, very basic level, nuclear fusion, we've got 4 single hydrogen atoms colliding with enough force. So these would be on the product side, or I'm sorry, the reactant side. And on the product side, we're going to have 1 helium atom and a whole lot of energy release. That's the very basics about nuclear fusion. If you have questions about this or anything related to it, please don't hesitate to ask.